so significant যে বোলজম্যানের গ্রেভর যে টুমস্টোন থাকে তার টুমস্টোনের উপর একটু লেখা আছে। লেটস সে একটা বক্স আছে, আই এম শুটিং at this box randomly, just randomly shooting on this box, on this area with a gun. What is the probability that my bullet will fall in this area? Let's say area of the box is A, or area of A. Our total bullet, the bullets are falling in the bigger area, definitely, everywhere, and randomly, uniformly randomly. So sometimes here, like this. What is the probability that the bullet will hit this circle? Can you guess? At least probability to proportional to ki hobo? Proportional to area hobo. The one dangor area, chances of bullet falling inside that area is higher. So probability area proportional hobo. Now, this is my total area. Aru ইয়াত পড়ার probability hobo এই area লগত proportional. Favorable probability always হল আমার কিমান মানে outcome কিমান favorable আছে divided by total cases. So ইয়াত favorable হল this area. So probability hobo favorable proportional. So probability is proportional to area. So probability of falling into this area is proportional to this area. Probability of hitting anywhere in this area is proportional to the bigger area. So probability of hitting this area, when we ask, is just this favorable divided by total. Now, if I say that at a point, just a point eta ase yat, let's say, hit korar probability kiman hobo? What will be the probability that the bullet will hit this point? Now, point or area kiman? 0. So it's a 0 probability. 0 probability that it will hit exactly that point. Okay. You have to give some small area to get a probability. Continuous probability. So continuous probability is always there will be a density, and you have to give some either length or area or volume to get some probability. Yet, for example, eta ball roll kori asu moi. The ball is rolling, and there is a probability of finding the ball here or here or here, anywhere. But if I ask, what is the probability of finding the ball exactly at x equal to 5.5 meter? That will be 0. That will be 0 because it is to and fro moving. There is a certain probability everywhere, and that probability increases. If I say what is the probability of finding it between x equal to 4 and x equal to 5 meter, definitely some probability. So this probability is proportional to this length, let's say delta x in this case, and total probability is proportional to, so anywhere, the probability of this being anywhere is 1. So actually your probability will be proportional to this. In this case, if total probability is something, that divided by length is called probability density now. So probability will be your, let's say, probability density times the thickness where you want. So if you are asked what is the probability between 0 and 1, then you have to take 0 to 1 here. So 1 multiplied by the density gives you probability. So therefore, if you reduce this thickness to 1 point, so the x is 0, so probability of finding something in 1 point is 0. Okay. It is different from discrete probability. In case of discrete, it can take one single value because the outcomes are discrete. So a dice, for example, 1, 2, 3, 4, 5, and 6. These values can occur, single value. But in case of continuous, it's different. Okay, we have to talk about density and then either thickness if it is one-dimensional, area, dA, if it is two-dimensional, volume if it is three-dimensional. So Yes, so this is the basis of thermodynamics really. So one main postulate of statistical mechanics is that probability is equal for all possible microstates. So let me really elaborate that. First, let me define microstate. Microstate, so macrostate first of all, is any. So eta moi dice throw korisu. And there are 6 possible outcomes. Yeah, moi koisu je either 1 or 2 or 3. Ahile I'm happy. Okay? Is either 1 or 2 or 3. Or 2 or 3. Jekono tinita ahile I'm happy. These 3 different possibilities are microstates. But ami differentiate no koru. For me, 1 or 2 or 3 is the same thing. Okay? This same thing, when I say either this, together it's called a macrostate. Tar mazot 1 ahile, 2 ahile, 3 ahile, I'm differentiate koribo nwaro. Okay? Then this is called a macrostate. Aru tar mazot 3 microstate ase. Now, obviously either 1 ahibo or 2 ahibo or 3 ahibo or any other. But he is 4, 5, 6 are not allowed. Ahibo sake, but these are not. Amar heibilak ahile macrostate change hoi jabo. We can then differentiate. No, this is different. 1 বা 2 বা 3 ahile we cannot, and we say it's the same macrostate. But jodi 5 ahi jay, then it is not the same macrostate. Okay? So, according to this theory of a priori probability, a 1 or 2 or 3 probability same hobo. They all have the same probability. A priori probability. Itu intuition or pora hai. First eta ami intuitively etu ami janu je kono defect na thakile perfect tomar dice jodi hoy. Etia all possible bilakor same probability hobo. Okay? Defect na thakile. Now, then what we do the experiment. And then we see outcomes, yes, they are coming with more or less same probability. And we say, okay, our theory, our intuition is right. Okay. Itu asile eta dicer khetrot eta example of microstate and macrostate. Ami eta example belag disilu je okay, let's before that. So definition of equilibrium in terms of probability. Now think about this. Equilibrium, pressure, temperature, volume, number of particles, these are all thermodynamic quantities, right? Thermodynamics of tomaloge pai jai. Probability hol statistics or eta quantity. So ami eta mechanics, either classical or quantum mechanics, consider kuru, particles, or I'll consider those. And then I'll apply some probabilities theory, probability and averaging. And then I should find some quantities that are thermodynamic. Itu hol amar aim. Microscopic or pora, microscopic particles, classic mechanics or pora, I have to go to thermodynamics through probability and averaging. So in this case, the definition of equilibrium, the definition of thermodynamic equilibrium is that if the system is in equilibrium, all possible microstates are equally probable. So let me give you one more example. Let us consider a box filled with some gas particles. After sufficiently long time, they are in equilibrium. Let's say yat argumentor karne yat eta one particle ase, 2 number particle, 3 number, 4 number, 5 number. Okay, spread hoye ase. This is a macrostate. Jot mane we don't understand which one is what, but they are nicely spread and are in equilibrium. What equilibrium means? We can make copies of this where 1 goes here, 2 comes here, 4 is here, 3 comes here, and 5 is here. This is macroscopically indistinguishable. Same number of particles ase, volume same ase, amar pressure bilak same ase. We will see this indistinguishable from this. Okay? Then aru eta copy. Yat 5, yat 2, yat 3, yat 1, yat 4. This is again macroscopically, it is the same state. Thermodynamically, this is the same state. Okay? This way, think about really gas-filled box. So all these copies are, each one is a microstate. Is a particular point of ase, a particular velocity ase. This one is one microstate, this one is another microstate, this one is another microstate, and likewise, if there are 10 to the power 23 molecules, there will be 10 to the power 23 positions. Aru velocity o exchange koribo paru 10 to the power 23 times aru 3 karon vectors. Okay, eta particular karone tinita hobo position, tinita momentum x y z, px py pz. So all these n number hole 6n possible copies hobo. Then still each one will look exactly the same macroscopically. So their macro state, the number of particles same ase, volume same ase, each copies are okay. Aru ki hobo? Let's say energy same ase. We'll come to that. Energy same hobo kine no hobo. Maybe pressure same ase. So egula thermodynamic quantities. These are thermodynamic quantities. Egula same ase. Eta box lole. Then these things are same. This state that n equal to some 100, v equal to some 1 liter. Eta fixed hoi thakibo every piece or karone. This thing is called a macrostate. A macrostate is given by these averaged thermodynamic things. But bhitoro we can rearrange, and each rearrangement will satisfy this, of course. Have to satisfy. If it does not, then it is not a microstate of this macrostate. Okay, so there will be really huge number of possible copies, and these are all microstate. Now, the theory of a priori probability tells us that if the system, the macrostate, is in equilibrium, then each copy has equal probability of occurring. So, which means if I wait long enough, I should see all these copies happening. So, eta boxot ami enekoi jodi rakhi di aru equilibrium ot thake, it will keep changing their position. So, at some point I'll see this, at some point I'll see this. If I wait long enough, let's say huge age of the universe and even more, all these copies must occur, with same probability. When they will occur, I don't know. Maybe this will occur after 10th combination. This may be immediately after 1 second, but they will occur. So if this is the case, they can be in anywhere. Actually, they are allowed. It's not that just this position should be exchanged. This one is allowed to be here, anywhere. Right? They are free and in equilibrium. So even this one is possible. All of them here. This one is also possible. This is also a microstate. Then why don't we? So here is the question. Itu hol amar definition of equilibrium. The equilibrium ot thakile eta macrostate dia ase, number of particles dia ase, and tar corresponding huge number of microstates ase corresponding to this same macrostate, then if the system is equilibrium, each of them occur with same probability. Okay? Just like dice. So these are like each toss of the dice. Each phase will come at some day. Like maybe you are throwing, it's just coming 3, 4, 5, 3, 4, 5, 1. You don't see 6. But if you keep throwing, of course 6 will come, right? At some point, but it will. So that's the theory. Now, a very important problem and the question is, if this is so, then why don't we never see all the gas particles in just half of the box and nothing here? Because the particles are allowed to be anywhere. So why not all the particles at some point in the half of the box, left half of the box? This should also be allowed. And this should also have equal probability of happening, right? This is also a microstate corresponding to that macrostate. So now the problem is, yes, it also has equal probability. But compared to the other cases, it is really, really less probable. And that's why we don't see it. Let's see. So, consider just one particle. Eta particle, this particle has the probability of being anywhere. Just like the bullet, remember. This is now a volume. So, the probability for one particle, let's say for first particle, to be anywhere is proportional to V, right? For the next particle, again, independent, so that can also be anywhere, so it's also proportional to V. This way, for nth particle, also V. And আমি ডিসকাস কৰিছো যে ইন্ডিপেন্ডেন্ট যদি probability হয়, right into right, p, that discussion. So, probability of all the particles together কিমান হল এই গোটেখিনি তোমার v to the power n হব, right? Total probability to be anywhere. Now, etia, if we ask, the particle should be only in the left half. So if the particle we want only in the left half, then only left half of the volume is available. So the probability must be V by 2. And total probability of finding all the gas particles in the left half is kiman? Left half, to full, let's say, is V by 2 to the power n. So দুটার মাজত comparison করিলে ratio ললে just left half divided by full কিমান হবো? Half to the power, basically half to the power n or 2 to the power minus n. Now n যদি usual হয় 10 to the power 23, 1 mole 10 to the power 23 particles থাকে. Just put 10 to the power 23 here. That's like to the power 23. This is 0. The probability of 2 to the power, this number 1 and then 23 0 is essentially absolutely 0. If you even wait for the age of the universe will collapse, will be destroyed. Another universe will start and that will get destroyed. But still, it's that much long time and therefore, we don't see this happening. But in principle, this is allowed, possible. This is a classic example of thermodynamic probability and definition of equilibrium. So, microstate or macrostate roughly, right? Etia hol a concept. It's called a phase space. Phase space is nothing. It's just the space of microstates. So dicer khetrot phase space is just these numbers that are possible. 1, 2, 3, 4. But in our case, we are always dealing with gas particles and position and momentum. One particle, consider just one particle. It can have x, y, and z, 3 position coordinates and 3 momentum coordinates because it's moving inside a box or something. So usually it's not possible to draw, okay? If for space x, y, z, a point there will represent the position of a point at a fixed time, then another time, and then it's moving. But if somehow it's not possible to draw here, but that's why it's a mathematical space, px, py, pz aru tinita axis jodi thake, then we get a 6-dimensional space. Okay, impossible to draw, so I'll not try. Hey karone ami ki consider koru, let's say 1-dimensional case, just 1-dimensional motion. Let's say এটা bead আছে আর এটা string আছে, string or মাজত 1-dimensional motion হয়. Then we have just one coordinate and one momenta. This is easy to understand. We can get an x-axis, a px axis, and then if I put a point here, the coordinate কি মান হবো x, px. And that tells us exact state of the particle. Position ki ase, tar momentum ki ase, hoi gol. We know where it is and how it is moving. So at any other point, we will know how is it moving. So this gives us the complete picture of position and also its motion. Now imagine 3 dimension. So something like this. So other y, z will come, px, py, pz will appear. So imagine, just extend this. It's mathematical, so it's not easy to draw. That space is called a phase space. And just like this 1-dimensional case, 3-dimensional at a particular, amar complete state dibo, ei space of at a point akile. So a point, a space of a point represent what a physical at a particular position aru momentum. A 6-dimensional space hoi jabo etia jodi ami 3-dimensional eta body movement consider koru. Okay, 6-dimensional space. Aru jodi n number of particles hoy tetia 6n hoi jabo. So it's a abstract space jot mane 6n number of axes ase, 6n number of axes আর তাক এটা পয়েন্ট ড্র করিলে, নাও 6-dimensional space of এটা পয়েন্ট ড্র করিলে বেসিক্যালি এটা পার্টিকলর 3টা কোঅর্ডিনেটস আর 3টা মোমেন্টাম আমি রিপ্রেজেন্ট করিব পারো। এটি আর 2টা পার্টিকল যদি হয়, 2টা পার্টিকলর কারণে 6 আর 6 বেলেগ বেলেগ 3টা কোঅর্ডিনেটস 3টা মোমেন্টাম থাকিব। Then I can write 2 points in this 6-dimensional space, or আমি 12টা axis লই এটা পয়েন্ট আঁকি দিলে আহি যাব 2টা পয়েন্টৰ কারণে জাস্ট এটা রিপ্রেজেন্টেটিভ পয়েন্ট, রাইট? For example, এটা পার্টিকল আছে জাস্ট রেস্ট তার এটা 1-dimensional কেস মুভমেন্ট পসিবল অনলি ইন 1 dimension. Then এটা x axis আঁকি তাত পয়েন্ট দি দিলে হই গল। আরো এটা পার্টিকল আছে, let's say x2. So in আমার এই এটা x axis হল 2টা পয়েন্ট আঁকিলে x1 x2 we can represent these 2 particles, right, physical particles. Or I can just write an x1 axis, x2 axis, and then draw just one point here such that ইয়াত x1 hobo, let's say এইটোৰ ভ্যালু হল আমাৰ 2 আৰু এইটো হল 4 so এটা এক্সিস ড্ৰ কৰিলে কি হ'ব ইয়াত 0 লৈ 2 আৰু 4 দুটা পয়েন্ট ললে these two points will represent আমাৰ দুটা particle in one dimension or আমি এটা x1 axis লম এটা x2 axis such that 0 ৰ পৰা 2 0 ৰ পৰা 4 just one point tar coordinate kiman x1 x2 and this is equivalent to two particles or position paijam that's how etia momentum include kora aru eta axis ahibo px1 px2 then one point will represent position and momentum of both the particles right now imagine n number of particles tetia 6n number of axis jodi moi draw koru it's a conceptual thing think about it 6n number of axis if we can draw okay then eta point jodi moi hey space or draw koru just one point that will represent n number of particles or position aru momentum so this space where position momentum eke logote eta axis or draw kora hoy mane amar x aru y aru z kon space represent kore physical three dimensional space right aru eta time logai dile space time represent kore exactly enekwa ami jodi momentum bilako draw koru to he is to space hobo 6 dimensional etar karone it's called a phase space aru nta particular karone 6n dimensional space tar eta point or coordinate to 6n number of numbers thakibo ene ko thakibo eta point p hobo x1 y1 z1 px1 py1 pz1 x2 y2 z2 px2 py2 pz2 blah 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 xn yn zn pxn pyn pzn sorry 6n ta point mane coordinates thakibo just like amar position space of x y z thake a 6 dimensional space of iman khini tomar coordinates thakibo to represents one point and one point hey space of actually represents all the n particles in a physical space useful this is very useful you will know you will see so in a three dimension or volume element kiman hoy dx dy dz right that is volume element small volume element in three dimensional space etia 6 dimensional space etia ahibo momentum bela ko include korile hei space ot ami gamma di likhu etu to thakibo physical tinita coordinator karone dx dy dz aru tinita momentum or karone dpx dpy dpz etu hoi jabo this one single point it just one particular karone etia for n particles z space to hobo etu a 1 1 1 1 1 1 then 2 2 2 2 2 2 3 3 3 n n n 6n ta eneko thakibo and that will be your phase space to final n particular phase space tar volume element for just one particle ami consider koru ei phase space or volume element for this one is for one particle dx aru dpx ekalogote loi aho aru dy dpy aru dz dpz and let's say if I call this thing h this thing h this thing h then h cube hobo amar volume element or cell volume of a cell minimum cell ami ki hoisu je h hol amar etur minimum size that a minimum size consider koru right always নহলে তো 0 হই যাব so some minimum amount যদি minimum amount h হয় এই dx time dpx or Then our volume element to hobo h cube. Itu classical mechanics of our h2 jikono size ami lobo paro. You can take it any small number. Quantum mechanics I cannot. Can't to janasane. Why not? Why we cannot take any arbitrary small value of this dx dpx in quantum mechanics? Uncertainty principle. Because dx dpx must be greater than or equal to h cross by 2. So we cannot go smaller than this. Nature is like this. So quantum mechanics of AH2 Planck's constant hoye jabo, and it's really the minimum. You cannot go beyond this. And that's why mane quantum mechanics of a phase space to discrete hoye jay. This is phase space or concept. Macrostate, microstate koisu. Oh, eta ami actually explain korisu, but term to diya nai. Ensemble. Is eta macrostate NVE, let's say, আমি তোমাক দিছো n10 to the power 23 particle, volume আছে আমার 1 liter, আৰু energy sum এটা কিবা দি দিছো, and I said that this is the state of this system. Now you can prepare huge number of copies of this such that এটা copy অলপ microstate বিলাক change হৈ আছে. When you do all possible copies of all microstates, okay, then this collection together is called an ensemble. It's called an ensemble. Beleg type or ensembles ase. For example, sometimes energy is a fixed hobo, a condition to diya na thake. Energy may fluctuate a little bit. Tar karon hol mane really real world কেনেকৈ আমি এনাৰ্জি ফিক্স ৰাখিম, কাৰণ মই যেতিয়া কপি বনাম or any system অলপ এনাৰ্জি লিক হৈ থাকিব, ৰাইট, with let's say এটা ফ্লাক্স এটা থাৰ্মাছ ৰাখিলে গৰম পানীৰ ভিতৰত, এটোতো আর 1 বছৰ গৰম নাথাকে, ৰাইট, মেবি খুব বহুত ভাল এটা থাৰ্মাছ হলে মেবি 3 দিন or 2 দিন, তাৰপিছত তো অলপ লিক হ'ব. Perfectly isolated system to nohoy. Conduction no holeo, radiation hoy ulai jabo. Right? Radiation hobo. A radiation stop korar karone mirror thake. Mirror ei karone ei color thake flux bilak. Tate radiation to nohoy. Vacuum thakor dutar major. To vacuum thakile air or through the convection hoy na jay heat. Etia microwave hoy radiate hoy energy jabo pare. Hitu stop korar karone mirror color or glass thake flux bilakor bitorot, but still glass bilako perfect reflector no hoy. So enaka hoi mane some leakage thakiboi. So which means aru energy even leakage na thakilo energy precisely ami measure to koribo noaru. Perfect measurement of energy is also not possible. Even quantum mechanically to possible no hoy. And same quantum mechanics of tomar uncertainty principle, energy at time or mazotas. In that case, how can I say that energy is some constant value E naught? Ami disu agutekinir E naught hoi thakibo. In principle, energy value onu aru ami eneka fix mane calculation koribo noaru. So in that kind of ensemble where the energy has some allowed variation, so I say that okay, the state of the system is this, but the energy can be between E and E plus delta E. So delta is very small, but slight change. Then if this is the case, the N and V are okay. When all these copies are same, but some of them can have energy E, some E plus delta E, some maybe in between the two. This kind of collection, when energy is allowed to move a little bit, keeping the temperature fixed, it's called a canonical ensemble. And there is another kind, grand canonical, we'll discuss this much later. And in a microcanonical ensemble where E is constant like this, fixed, temperature has to be derived from this. In such ensembles, you can count how many microstates are there because we prepared copies, right? Turns out that tomar entropy ase je eta thermodynamic. Now yat ami duta part kori asu, just wait. On left hand side S is an entropy. An entropy is a thermodynamic quantity of a macroscopic system, while this omega is called number of microstates. So number of microstates, rearranging and counting. Okay, this is slight different rearrangement, counting, slightly different rearrangement, counting. This counting is coming from microscopic description or mechanics, classical mechanics or quantum mechanics. So on this side of equation, we have a microscopic description. And this is the total number of microstates that corresponds to or maintains the same macrostate. A condition to same rakhi kiman khini copies ase is called this omega, number of microstates. At this side of thermodynamics, etu Boltzmann দেখাইছিল যে প্রুফ করেছিল যে thermodynamic entropy is proportional to this number of microstates. Now number of microstates নহয় Boltzmann proof করেছিল যে এটো proportional to thermodynamic probability. Now number of microstates and probability are very related. For example, once again Dyson example, probability to কার লগত related, either 1 or 2 or 3 করিলে 3 times হয়ে আছে. So number of microstates ইয়াত কিমান তিনিটা, right? So তিনৰ লগত related 3 times হৈ যাব, 3 into 1/6. Sarit either 1 or 5 or 6 or 4 করিলে 4 times 1/6 হব. So our probability is proportional to number of microstates, and that's why Boltzmann দেখাইছিল যে entropy is proportional to log of probability, thermodynamic, and probability is proportional to number of allowed microstates or copies kiman ase, jitu favorable copies. Okay, so hey counting or aru probability, so tomar probability theory agote mathematics of clear thakile olop easier hoy, নহলে aru statistics thakile olop aru easier hoy, etia to statistics na thake. So microstate logot n correlation in equal to k ln omega. A k to k is a proportionality constant. We'll prove later that this is Boltzmann's constant kb. Okay, into n a important law actually, so significant যে Boltzmann যে tomb থাকে, Weber যে tombstone থাকে, তার tombstone এর উপর এটা লেখা আছে. This is so important. So S equal to k ln omega. Eto important মানে ইমান পাওয়ারফুল যে এই জাস্ট এটো জানিলে ইয়ার পরা আমি থার্মোডাইনামিক যে কোনো বস্তু we can derive. Temperature ইয়ার পরা আহি যাব 1/T is given by del S by del. এই del S পাই গলে ইয়ার পরা ফার্স্ট আমি জাস্ট কাউন্ট করিম. Just look at this. This is a counting problem. কিমানখিনি মানে কপিজ আছে 1 2 3 4, okay, these many counts ইয়াত বহাম লগ লৈ এটা k দি মাল্টিপ্লাই কৰিম, and that is my probability thermodynamic entropy পাই গলে del S by del A কৰিম, টেম্পারেচার পাই যাম, তারপরা ইভেন আমার pv equal to nkt আহি যাব, গোটে thermodynamics আহি যায়. Okay, just 1 minute. Phase space to বুঝি পাইছা. Let's just take one dimensional phase space. Just x aru px. This is very easy, right? Two dimensional karon mane x aru px, kintu ene x mane amar space hol one dimensional. So one dimensional px etu. Let's say etu eta phase space ase. Aru ami eta consider korim simple harmonic oscillator. So simple harmonic oscillator ki hoy, energy equal to half k x square aru half mv square or px square by 2m, right? Etu hoy amar simple harmonic oscillator energy. Now if I say microcanonical ensemble, then I say that E is constant. E does not change for all these copies. E constant mane this equal to some constant, and then x aru px or মাজত etu ki equation? It's an ellipse. It's an ellipse. You can bring it like some x over a square plus some px over b square equal to some 1. I can rearrange them and it will be an ellipse. So basically like this. Okay. Now, if E is fixed, that means our allowed values bilak এই ইলিপসৰ ওপৰত থাকিব লাগিব আমাৰ পাৰ্টিকলৰ পজিশন আৰু মোমেন্টাম এনেকুৱা হ'ব লাগিব that it's only should be here or here or here or here, it cannot be here. ইয়াত হলে কি হ'ব এই ইকুয়েশন স্যাটিসফাই নকৰে, so only these are allowed. This thing is called energy surface. ইয়াত তো সারফেস নহয়, ইয়াত তো লাইন এটা, বাট তোমার যেতিয়া আমি 2 ডিমেনশনত যাম এটো অ্যাকচুয়ালি এটা ইলিপসয়েড হৈ যাব। 3 ডাইমেনশনত গলে হায়ার ডাইমেনশনাল ইলিপস হ'ব, এটা abstract mathematical space, but এটো এটা সারফেস হ'ব or volume. So that we say energy surface or ergodic surface. It's an important fact. আৰু আমাৰ allowed value বিলাক, so now copies বিলাক যদি লৈ মই বেলেগ হারমনিক অসিলেটর, এটাত x অলপ বেলেগ হ'ব, তার p ডিফারেন্ট হ'ব, আৰু এটাৰ x হায়ার হ'ব, p কম হ'ব, আৰু এটাত x মে বি বহুত সৰু, p বহুত বেছি, but they will satisfy this equal to 1. And so that means আমাৰ এই স্পেসৰ এই যে আমাৰ এটা মাইক্রোস্টেট আছে এটো এনেকুৱা ঘূৰি থাকিব, it will move on this surface. Any point you take here, it will correspond to a particular microstate. A point here will correspond to another microstate. In continuous cases like this, amar infinite number of microstate basically, right? Continuous, so there is no possible value over here. Okay.